Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program.
Today I will talk about dark energy and the accelerating universe. So I will start out by saying that the universe today presents us with a great puzzle. What is 95% of the stuff in the universe? Amazingly, we still don't know the answer to this, and we are working toward that answer, and I will describe what is going on. So let me jump to the bottom line right away. This is the makeup of the universe today. And here you see some familiar components. You see visible matter. This is all the stuff you see when you look in the sky, either by naked eye or with a telescope. It only comprises 4% of the total by energy or by mass. In fact, stars are only about 0.4% of the total, and gas is a little more than 3%. Then a bigger, more dominant component is dark matter. Now, dark matter is something that most, if not all of you, will have heard of. It is matter that doesn't shine, it's dark. It's probably an exotic type of elementary particle. Dark matter has been suspected since 1930s in the work of Zwicky. We've heard at least one lecture here about dark matter in the Saturday morning series. Dark matter, not everyone believed Zwicky, but it's really since 1970s or so that dark matter has been pretty well established. And nowadays we know it's there. We don't know what particle is responsible for it, so it's pretty mysterious. And so dark matter is about 20% of the total. In fact, it dominates over visible matter by about 5 to 1. And then also we have a small amount of radiation today. Radiation is really photons, particles of light. Radiation used to be dominant in the early universe. Nowadays, it's subdominant, as you can see. And then the biggest component that I will talk about today is dark energy. It comprises about 3/4 of the total. It dominates over both dark matter and visible matter. It's been suspected that something is amiss since about 1980s, but nobody was sure. And a real direct evidence for dark energy comes in 1998. Now, to go over some basics of cosmology that we will need to understand what our universe is doing. Universe is, according to the best of our knowledge, homogeneous and isotropic. Homogeneous means it looks the same no matter where you are in space. You look around, it looks the same. And of course, if you look around this room, it doesn't look the same in all directions. If you go out in the solar system, it doesn't look the same in all directions. And even if you're in a galaxy, it doesn't look the same. You can be look through the plane or outside of the plane of the galaxy. So in fact, this means homogeneous only when you go to large enough scales, look at big enough chunks of the sky and enough galaxies, then on average it looks the same anywhere you are. And it's also isotropic. This means it appears the same in every direction. So in fact, these examples I gave refer to isotropy. No matter where you look, it appears the same. So here are some examples of galaxy distribution in the sky. Here, this wedge that you can't see so well. The wedge is only the effect of where this particular telescope observed. But if you look anywhere within the wedge, we are in the middle, it looks on average the same. Likewise, if you look at big chunks of the sky through a telescope, they look the same. So universe is homogeneous and isotropic. Moreover, universe is expanding. Now, this is a well-known fact to everyone, and it's been known since the 1930s and the work of Edwin Hubble. What Hubble did is the following. Hubble looked at distances to what he called nebulae, which nowadays we know as galaxies. So he looked at some galaxies that nowadays we'd consider them to be pretty nearby, but at the time they were considered to be very far away. And he measured those galaxies, and then he measured velocities with which those galaxies are moving with respect to us. And he made up a diagram that's called the Hubble diagram. So in fact, the way he measured distances is he found these things called Cepheids. They are variable stars. They are stars in these galaxies that pulsate. And if you measure pulsation period, that's related to the brightness of that star, which then can be related to distance that you can measure from the galaxy. So I won't talk about that too much, but he had a clever way to make up the velocity distance diagram, and then he realized the further away the object is, the faster its velocity away is from us. Now this exactly is the statement of the expansion of the universe. The universe is expanding, and you can see that, the Hubble law holds. You can imagine, I think there was a demonstration maybe last week or 2 weeks ago, when you blow up the balloon and you have a colony of ants. Each ant city gets further away from another colony of ants on this balloon as you blow up the balloon. So likewise, in three-dimensional space, the universe is expanding, and all galaxies are any galaxy is getting further away from any other galaxy. In fact, because of this expansion, there are some interesting effects. If you imagine matter particles in the universe, they dilute. So if you double the number of particles is conserved. They don't just get created out of nothing. So if you double the volume, you have the number of matter particles in that volume. So you have the energy density in that volume. So we know very well how matter scales. And it's interesting to consider wavelength of light, or particles of light, or photons, or radiation. What happens is not only do they dilute, as does matter, they also get stretched. And when you stretch the particle of light like this, it loses energy, because wavelength becomes longer, frequency becomes shorter or smaller. So the energy of light, in fact, falls off even faster than energy density of matter, because it gets diluted and it gets stretched. Now, the radiation redshifts. In fact, what does a redshift mean? Well, redshift is a very important concept discovered about 100 years ago. And what happens is that when you see light from distant objects, that it's emitted at some frequency, but it gets stretched as it travels to us over great distances and long amounts of time. And when it reaches us today, it's longer than it was at the beginning. So in principle, you can have blue shift or redshift, but what you see from distant object is almost always redshift. It emits a frequency at some light maybe of a certain frequency, and we see it in another. We see it more shifted toward the red. Now it turns out that 1 plus redshift is actually the size of the universe today divided by the size of the universe then, when the light was emitted. Okay? So for example, redshift of 0 is today. Redshift 1 means that the universe was 2 times smaller then than it is today. It's 2 times bigger now, because this ratio is 2. Okay? So redshift tells us how much smaller the universe was when the light was emitted from that object. And it's actually fairly straightforward to measure, because what you do is you look for emission lines from some object. You know some element, whatever your favorite element emission line is, it's in the lab. You observe some frequency from this object, and it's not the same, and you do division of those two frequencies, and you get the redshift, 1 plus redshift, okay? So if some frequency was 1,000 angstroms and you observe it at 2,000 angstroms, you're looking at the object at redshift 1. Okay. Now let's do a quick whirlwind tour through the history of the universe from the Big Bang until today. So in the beginning, there was Big Bang at time equal to 0. Expansion starts, and as many of you know, it happened not here, not there, but everywhere. Details are not very well known of what happened at the Big Bang. It's currently beyond reach of any cosmological probe. We are talking at time 0, an infinitely small size, infinitely high energy, and please don't ask what happened before the Big Bang. We don't have any idea actually what happened before the Big Bang. There are theories. There are various theories about what could have been going on before. They are just theories right now. There's no way to decide at this time at least. Okay. But amazingly enough, now we are down to one of the triumphs of human mind. We actually have quite a good idea of what was going on at the earliest moments after the Big Bang. Tiny, tiny fractions of a second. We've had very high energies and very exotic physics. And here I won't go into all details, but there are some uncertainties. Was grand unified theory at play? A theory that unifies all 4 fundamental forces? Quite possibly. String theory is at play. This was subject of Sarah Cremonini's talks a few weeks ago, and quantum gravity. So these very difficult to work with and exotic important theories were at play at the very early universe. There was also inflation a bit after a period of very rapid expansion of the universe that I will mention a bit later. The important thing with inflation is it laid out density fluctuations in the universe. So the same fluctuations that say a little denser here, a little less dense there, those fluctuations grew to become galaxies and clusters of galaxies and objects we observe on today. So they were seeded or laid out by inflation, or so we think. Then, at about 1 second after the Big Bang, we had a quark soup before, and then at about that time, quarks combined into protons and neutrons. So quarks are the smallest particle constituents we know of. There's 6 of them, and they carry funny names as up, down, charm, strange, top, and bottom, or beauty. There are 6 quarks, and they were actually, the energy were so high early on that they were floating around, but at about 1 second they get combined. And so here we have this happens at times of about 1 second. Then at about 3 minutes after the Big Bang, we have what's called Big Bang nucleosynthesis. Nuclei form out of neutrons and protons because the energy has fallen enough for this to happen. And in particular, hydrogen and helium nuclei and very small quantities of a few other elements form, but these two completely dominate. Universe at this time is very solidly dominated by radiation, by photons, right? It's full of radiation. And universe is opaque. These photons do not go far. They scatter off electrons, so the photons are just bouncing around, hitting other electrons at this time. The next important moment is 300,000 years after the Big Bang. Now, at this time, universe is matter-dominated, but it's not really matter domination that's interesting about this time. Matter domination actually happened earlier, the equality. At this time, matter to radiation is maybe 10 to 1 or so. Matter dominates, though not completely. What's important in this time is that atoms form. Radiation is free to propagate because free-floating electrons and nuclei combine into hydrogen atoms, and now the radiation doesn't bounce around anymore. It just flows freely. So if you are a photon, a particle of radiation, particle of light at this time, you're not scattering anymore, and you just keep going. And the next thing you see is 30 million years later is our telescope, our detector. Right, that's what you see. We in fact observe cosmic microwave background, or CMB, radiation that comes from this time. Now at this time, so the temperature today of that radiation is about 3 Kelvin. This is when universe was 1,000 times smaller. And so the temperature at the time was actually 3,000 Kelvin, 3,000 degrees above absolute zero. It was still fairly hot by our everyday standards. Now, this radiation was uniform, but only to 1 part in 100,000. So let me show a graph of cosmic microwave background radiation. Here's how it looks. It's really not that interesting at first sight. It's spectacular that we observe it today. Its observation got Nobel Prize about 3 or 4 decades ago by Penzias and Wilson. Its temperature uniform to exactly this many Kelvin, so about 3 Kelvin about absolute zero. So this is a CMB radiation. Now it turns out it looks uniform, but it's only because our eyes are not good enough. In fact, there are fluctuations 1 part in 100,000 on top of this uniform temperature. And amazingly enough, we are able to observe those fluctuations. You have to subtract this mean temperature, and you're left with this. So this is, in fact, now the little wiggles around that mean temperature as observed by WMAP experiment. The first observation of a much cruder resolution of these won Nobel Prize, I believe, last year by the Kobe experiment, and this is from another experiment called WMAP. So these are hotter and colder spots, and the stuff you see in the middle is just the fact that we look through the galaxy. So for this talk, we're not interested in what just around us, we're interested in this real thing that comes from the early universe. So these fluctuations are the same ones that were laid out by inflation. So this is coming to us from redshift of 1,000 from time of 300,000 years after the Big Bang. Then we step forward to time. In time and now we are 1 billion years after the Big Bang. Now the universe is dark, matter dominated, and it's just called the Dark Ages, this period. It turns a little bit after that is when first stars and first galaxies form. And that in itself is a subject of our research. They light up, and then the next thing they do is they ionize the universe. They ionize hydrogen atoms, the light from these first stars and galaxies, in a process that's called reionization, for those of you who are interested in this in more detail. So this happens when the universe was maybe just a few billion years old. And now we jump to the modern universe. 13.7 billion years old. First of all, notice the amazing accuracy. It's a true accuracy with which we know the age of the universe, another triumph in my mind of modern cosmology. In fact, we know this age precisely from the structure of the hot and cold spots of the cosmic microwave background map that I showed. Right? Very precise, to a few percent we know the age. Stars, galaxies, and clusters are everywhere. And on top of that, there's dark matter that we can see, dark matter. Universe is matter dominated. So if I'm taking a course on hearing a lecture in this in 1995, I'm told universe is matter dominated, period. Okay? But we have a big surprise coming to us. Now, before I get to the surprise, let me mention a few more things. In particular, Einstein's theory of gravity, very successful theory, general relativity, or GR as it's known to experts, 1915 or 1916, and in a verse, matter tells space how to curve, space tells matter how to move. So it's a very mathematical set of rules that tells us how laws of gravity act and how matter moves under those laws of gravity, and also likewise how the space itself is curved. Now, one of the implications that has to do with general relativity is that geometry is destiny. Again, this is something that many of you have seen. It's not really news. Homogeneous and isotropic universe can be of three kinds. Can be flat space with zero curvature, positively curved or spherical space with positive curvature, and negatively curved hyperbolic space. So flat space is like a flat sheet of paper. Two parallel rays continue to be parallel. Positively curved space is the one where two parallel rays converge. So this is like surface of a sphere. In positively curved space, sum of the angles in a triangle is more than 180 degrees, not equal to. And negatively curved space is like a surface of a saddle. Two parallel rays diverge, and the sum of the angles in a triangle is less than 180 degrees. Okay? Now, geometry is destiny. The standard story, if I'm listening to this in 1995, there's no asterisk, there's no small print, because nobody bothers about small prints, means flat space, that kind of universe expands forever, but barely. Positive curvature, positively curved universe recollapses eventually in a big crunch. And the open universe, or the one with negative curvature, expands forever, period, right? So if we can measure curvature of space, if we can measure which one of these, we can find out the ultimate fate of the universe. Notice a small print. This is in the matter-dominated universe. But remember, people usually don't worry about small prints. They don't read them. Okay, so this is in, even up to the mid-90s, this would have been the story. So then, if we are able to measure which one we live in, we can decide for the fate of the universe, which is a useful thing to know. Okay, now, before even we get to any kind of measurements, inflationary theory of the early universe has a prediction. Inflation says that universe has been expanding very rapidly early on, and there are reasons. Inflation solves some very important problems in cosmology that I won't quite get into. But one solid prediction of inflation is that universe is expected to be exactly flat, zero curvature. And here's the reason. It can actually be understood quite simply. Imagine a colony of ants living on the surface of a balloon, again, our favorite example from one dimension less. And imagine you blow up that balloon by a very large amount. Then, if you're a colony of ants, you can't see too far on this balloon, because even from your, whatever the beginning of your own Big Bang, you only light only could have reached you from a certain area, certain distance away from you. And remember, you blew up this balloon to a gigantic size, absolutely gigantic, right? Much bigger than the area you can see. So if you look around, even if you have a perfect telescope, the furthest you can see if you're an ant is this far away. And you look around and you see flat. The reason this balloon is so big, it was blown up by so much that what you see is perfectly flat. This is very much like, us being here on the surface of the Earth and thinking the Earth is flat. As far as you can see by naked eye, it looks just flat, right? So you need to be in a gigantic balloon, and inflation does this for you. It really, blows up space by a huge amount. So inflation predicts that now in one dimension more, if we look around us as far as we can see the best telescope to our observable sphere, which is called the Hubble volume, it's going to be perfectly flat. Now, of course, inflation is theory, and we'd like to check this with data if at all possible. We'd like to measure curvature of space and decide between these two possibilities. We'd like to decide, in fact, if it's open, flat, or closed. Now, it turns out one way to decide on this geometry of space is to measure distances to distant objects, okay? So you do the following. You measure distance to the galaxies away from us and plot it as a function of redshift. So remember, this is nearby, and then as you go to further redshift, this tells you how much the universe was smaller when the light was emitted than it is today, right? So this is a measure of distance. Right? Distance and time are very much related if you talk about cosmology. So, for example, if you're at redshift of 1, you're looking so far away when the universe was, when that light from that galaxy was emitted, was 2 times smaller than it is today. Okay? So if you measure this, cosmological theory tells us that open, flat, and closed will predict different curves. So if you put data points here, distance versus redshift of different galaxies at different redshifts, they'll line up with one of these curves. Okay? And then we can decide if we live in open, flat, or closed. And I guess ideally we live in a flatter, matter-dominated universe, which inflation predicts. The problem is that distances are notoriously hard to measure in cosmology, or in astronomy rather. This is a very old problem in astronomy. It's not new. You can measure redshifts from the spectral lines that I mentioned quite accurately. But if you just look through a telescope and see a blurry galaxy, it doesn't even have to be blurry. How do you know the distance? Right? That's very hard to measure. So measuring this is a key, and that's a big problem. Oh, and for those of you who are aficionados of cosmology, there's an interesting little fact. Hubble law, remember Hubble did a similar thing. He plotted distance and velocity, but velocity is related to redshift. Hubble plot that he made is right here. At very low redshifts or low distances, you see it's a linear curve, and these possibilities diverge only at greater distances. So Hubble plotted this part right here, and the slope of this curve is the Hubble constant. It's the rate of expansion of the universe, just for those of you who are interested in this. But now we'd like to extend this Hubble curve to much greater redshifts and distances. Okay. Now enter the picture type 1a supernovae. Now you're probably wondering, okay, I'm going to talk about these funny objects, type 1a supernovae. I just talked about distance, and the talk is about dark energy. How are those related? And they will all come to talk to each other very soon. So type 1a supernovae are events that happen where an object that's presumably a white dwarf, this is a very massive star, it accretes matter from a companion star. And so it accretes, and it goes over a certain limit, then it explodes. Now these explosions are tremendous. They can be seen to the edge of the universe almost, so to speak. And so one feature of these events called type 1a, 1a is a specific type of a supernova that we will be especially interested in. They can be seen to great distances, these explosions. Okay, so let me say a little more about this. So I already said this, when the mass goes over a certain amount with that accretion, then there's explosion. And when the explosion happens, the supernova can be as bright as a whole galaxy. Here's a supernova, here's a distant galaxy in which that supernova is found. This may not sound too surprising until you realize that a galaxy has 100 billion stars. And one of them will shine almost as much as a whole galaxy when it explodes. That's how bright they are. Now, why are we worried about, why are we talking about them? So I have a movie here that I will repeat once again. So here we see, this is a light we see of supernova going up and down. The period for this whole thing is about 2 months, a couple of months. So you come back every few days and you see more and more light, and then you see less and less light from a supernova. This thing here will show the frequencies that are excited during the explosion. And please pay attention, here's a galaxy from which the supernova comes, and supernova will be right here where I'm pointing now, and you'll see it go up and go down as the explosion happens. So let me run that again. And so you can see the explosion go up and then go down, this is the amount of light you'll measure. So this is the type of thing we observe. Now, why all this business looking at these explosions? And the reason is type 1 supernovae are very special. They are very nearly something that's a prized commodity in astronomy, and it's called the standard candle. Standard candle is an object whose intrinsic luminosity you know. And very much here you can use parallel with lights of a car. If you are, say, in the night and you see lights from a car, car lights, if you knew that this is maybe Ford Taurus or some car, and you knew intrinsic amount of light that its light bulb emits, then just by using inverse square law, just by using very simple physics, you'd be able to decide how far away that car is, right? So if you know intrinsically how bright it is, then you can tell how far away it is. Otherwise, you can't, right? You don't know if it's a strong light far away or weak light nearby. But if you know the intrinsic luminosity, then you can decide. And so objects of whose intrinsic luminosity you know something about are called standard candles. Okay? Now, again, this is the same thing, standard candles, type 1a supernovae. You measure flux from them. And if you know type 1a supernovae all have very nearly the same intrinsic luminosity because they're the same when they explode, to a first approximation. Therefore, just by comparing the amount of light from them, you can determine the ratio of their distances. It's like seeing two cars. If you know it's the same car and you measure two brightnesses, then you can very easily decide what their relative distances to you. So by measuring the flux of these, you can determine the relative distances to these supernovae. This is key. And then remember, to make up our Hubble diagram, distance versus redshift, you measure shift of spectral lines from that supernova, so you measure its redshift. This is almost considered to be more straightforward, even though any astronomer will tell you that's not so easy either. But the key is this distance. Okay, so people have done this. Now there's a problem. If you point your telescope to a galaxy and wait for supernova, you'll have to wait 5,000 years. And even if you follow healthy living, this might be too long. You may not live long enough to wait for this. So what's to be done? And here the solution is messy. There's no clean solution. Combination of using world's largest telescopes, scheduling them in a coherent way, and then what's called following up supernovae, which means come back every few days to see that light go up and down. That's how you can most accurately measure the amount of light. And then most importantly, heroic hard work by two teams of supernova researchers. One of them led by Sol Perlmutter. It's called Supernova Cosmology Project. And one of them led by Brian Schmidt, high redshift supernova team. So two teams of people around the same time in the mid-90s have been doing this. And they figured out how to get around this very prosaic problem. Okay, so starting in the mid-90s, they made up a diagram, and here's a slightly blurry version of it. Let me explain what's plotted. This is the same Hubble diagram, but I changed units here a little bit. So this is log of the distance. So this is like the distance. And don't worry, it doesn't look the same. For those of you who like mathematics, this kind of thing, I take a logarithm. Anyway, just look at the relative case where these curves are. And this is redshift. So this is very nearby objects, and this is as you go out to a redshift of 2. These are actual data from supernovae. And for those of you, again, more interested, they are binned. So there's more supernovae than this, but I combined them into maybe a few meta objects, so to speak. Now, notice the amazing thing they saw. Open, flat, and closed cases that I mentioned before, neither of them fits the data at all. And if you do statistical analysis, they're so far off. They don't fit the data at all. What fits the data, funny enough, is a case where universe accelerates now and decelerated in the past, and the one that always accelerates. Now, imagine an analogy here. Imagine car is approaching to you. We are in a car country here, so we have a car again. It's approaching you, and you tape it with a camera. And then you roll back your camera film, and you're looking at different snapshots of where the car was. Okay, so this is like looking at different supernovae. You take up slices. Now, if you roll back film and you see the car is here and the car is here, and what you see is the car at any given distance is further away than you would have expected it to be. So it's like you would have expected it to appear, but in fact it was here. What does it mean? It means it was accelerating, right? It was making up that distance faster than you would have expected with a constant speed. So it just is further away at any given point. So likewise, they found that these supernovae are fainter, which means further away than they would have been in these cosmologies that we expected of open, flat, and closed. These are all matter-dominated universes. So the universe cannot be matter-dominated. None of the matter-dominated option fits it. Just completely off. So universe had to be speeding up recently. Okay, so this was a momentous discovery. This discovery, this concept of accelerating universe is called by something that we don't understand very well so far, and it's called dark energy. It was named by Michael Turner from University of Chicago, who is also a prominent theoretical cosmology researcher. So universe is dominated by something other than dark matter. Dark matter, visible matter, all that stuff would be one of those green lines. It doesn't fit. The new component called dark energy makes universe expand faster and faster, speed up, or accelerate. We know it's smooth, and I'll come back to this. Unlike dark matter or visible matter, it's almost or exactly smooth. And we don't know too much other than that. So the picture we have, I'll run a movie, is we have Big Bang, very quick zoom, galaxies slowing down, and then at some point, they speed up again, right? And they spud. So maybe let me run it just once again, just in case we have. So they slow down, slow down. We thought they were going to be slowing down forever, slower and slower. But the funny thing is what happens now is the universe starts expanding faster and faster. Again, for those of you who like this, it happens about redshift less than 1. So quite recently, when a few were maybe 5 billion years old or so, 5 to 10, I don't know exactly, is when it starts, which is very late, given, remember that history that had a tiny fraction of a second, minute, this happens at a few billion years. Okay, contrast that case with dark matter. Don't confuse dark matter and dark energy. Dark matter is exotic matter, but it's matter. It clumps. And so anytime you see a galaxy in the sky, what you see is this. What really you should be seeing, but you're not seeing, is there's a blob of dark matter around that galaxy. And so it's called the dark halo. This is called halo that's around the galaxy. And so dark matter clumps, maybe galaxies will have these halos of dark matter. Clusters of galaxies that Elena Rassia talked about also have dark matter in them. But dark matter is not smooth. It clumps. And maybe most of the time there's a lot more dark matter than visible, maybe 10 to 1 or 100 to 1, maybe 1,000 to 1 in some cases. But it's pretty smooth and it clumps. And dark energy is something that's almost perfectly or exactly perfectly uniform in space. We're trying to decide at the forefront of research now which it is. But it's certainly nearly smooth. Actual photo of dark energy, there's... I don't have any demonstrations, probably, as you can notice, for the same reason. We don't, it's everywhere around us in a small quantity, perfectly uniform, there's not much to see, even less than for dark matter. So let's see, consequences. It's implied by supernovae, but now there's a very strong argument. Say some of you say, well, this supernova business with standard candle is just very funny. I don't believe any of it, I don't believe it. I know they've done a good job, I don't believe it. Even if you completely throw out type 1a supernovae through the window nowadays. So this wasn't the case in 1999, but it's the case today. A variety of other cosmological data firmly points in the direction of dark energy, even with no type 1a supernovae. So this is a very strong argument that we have something. And they agree. The two agree really well. It makes the universe older, so this is now coming to consequences. Without dark energy and with the same amount of matter, the universe is maybe around 9 billion years old. With dark energy, it's about 14 billion years old. So it makes the universe older, as it turns out. It pushes things apart at large distances. It doesn't push the stable away from you or anything, but you have to go between the galaxies, and then they're being pushed apart. And the discovery is absolutely revolutionary. It's one of the greatest discoveries of the 20th century, probably. It happened exactly 10 years ago, so feel free to go out and celebrate tonight. 10 years, 10 years of dark energy is this year. Now, let's move to theorists' land a little bit and see what are the candidates for this, what's going on. Well, quantum mechanics actually predicts something that behaves very much like dark energy. It predicts that vacuum or empty space has energy. And it turns out, you can just trust me on my word, that vacuum energy will do exactly this. It'll push things apart at large distances. It'll very much behave like dark energy. So quantum mechanics says that in empty space, you can have two particle and antiparticle pop up of empty space and annihilate a moment later. This doesn't happen very often, but it happens. It really happens. And so this type of creation annihilation will actually make a vacuum, empty space, have certain kind of energy that'll be different from the usual matter. And now you can compute how much of this vacuum energy that would fill the role for dark energy we should have. And this is one of the amazing discrepancies between theory and experiment. Quantum mechanics predicts a number 120 orders of magnitude bigger than dark energy that we measure. Not 120 times, 120 orders of magnitude, this much big more than we measure. Okay, so what is going on? Quantum mechanics predicts a huge amount of vacuum energy that would, make the universe last a very short period of time. We would definitely have no life. So you say, okay, something here is wrong. Quantum mechanics is correct, but maybe this particular aspect is not right. We need maybe string theory. So you say, okay, it's not this, it's 0. But it's not 0 either. It's 1 in these units. It's a tiny amount, but it's definitely not 0. 0 would be no dark energy. Okay? So this is a very famous problem, a mystery number 1 of dark energy that goes under the name of cosmological constant problem. The cosmological constant is a term that Einstein introduced in his equations of general relativity, then scratched it off very famously and called it my biggest blunder. And in fact, vacuum energy would behave just like that term. So it would appear Einstein is right, but we predict much, much, much more. To put this number in context, the number of protons in our observable universe is 10 to the 80. It's 80 zeros. And this number is 10 to the 120. It's 40 orders of magnitude more than the number of protons in the universe. That's how big the discrepancy is. The other famous problem, just a little less famous, but still famous, is why now? Why do we just happen to live at a time when dark energy starts dominating? So I made up a little graph here. Here's today, and here's going back in the past, and here's going back in the future. And here's the energy of different components, energy per volume, so energy density. So remember I told you matter gets diluted by the expansion, remember? So it's energy goes down as volume, energy per volume. You double the volume, you halve the energy density of matter. And dark energy, you can trust me on the fact that the implication of these measurements is that its energy density is either exactly constant in time or nearly the constant. If you had energy of the vacuum, it's easy to understand that no matter how you expand or shrink the universe, per unit cubic yard, you will have the same energy. So its energy is constant. And from the measurements, it may not be perfectly this, it may wiggle around. Notice I couldn't draw I couldn't draw a gigantic graph, so I'm telling you that there are many, many orders of magnitude here. Remember, this is 380,000 years, 1 second. This is a tiny fraction of a second. So there are many, many orders of magnitude here difference. So matter was completely dominant early on. If you lived somewhere here, all you'd see is matter. There would be just a super tiny amount of dark energy. If you extrapolate in the future, just extrapolate these two curves, dark energy completely dominates. If you live in the future in 50 billion years or some, all you see is dark energy. There's no matter in sight. So why do we just happen to live at an era when, remember, they're 3 to 1 or so. They're 76% and 20%, 25%, right? So very roughly, 3 to 1, which is very close to 1 to 1. We just seem to be living in a special era when we can see both of them. Nobody knows why. And this is called a coincidence problem. Why now? Why do we live now? Okay. Just to illustrate that coincidence problem, here we are now. Here there's a past, and here's the future. Blue is dark energy, red is dark matter, and yellow is observable matter, visible matter. And so today it's 3 to 1. You go to the past, and this is even just when the size of the universe is 1/4. All you see is red. You go further, all you see is red and yellow. All you see is matter. You go to the future, all you see is dark energy. So why do we just happen to live when they're all beautifully separated? Two famous problems. Okay, so now we have famous people being very confused. Steven Weinberg saying this is a bone in our throat. Frank Wilczek saying fundamentally maybe the most mysterious thing. Ed Witten saying it would be number 1 on his list of things to figure out, and he's very smart, so this is quite something for him to say that this would be number 1. And Michael Turner saying this is the biggest embarrassment in theoretical physics. So this is people really, even some of the smartest people, completely confused. As you'll notice at this point, I have a lot of questions and I have no answers, not because I'm hiding them, because nobody knows the answer to them. Is dark energy vacuum energy? Is it actually the case that Einstein's general relativity is modified? We are working with a slightly wrong theory. So we are maybe using the wrong equations, and if we use the right equations that somehow were different on large scales, then we would, we actually it appears to us that the universe is speeding up, but it's not speeding up, we are using the wrong equations. Well, that would be bizarre. The general relativity, at least in the solar system, has been phenomenally well tested. But it is possible, because at this point you invoke any possibility, right? No matter how weird. Or is it perhaps dark energy is a funny fluid that fills up the universe? This is sort of standard modus operandi for some people. Or is it something completely and utterly unexpected? Okay, so this is all kinds of questions, what is going on? Now, there are some very bizarre consequences of dark energy, and amazingly enough, they are true. So first of all, geometry is not destiny anymore. So remember, flat expands forever barely, closed recollapses, and open universe expands forever. Now you can have, it's not true, you can have any possibility. You can have open universe recollapse, you can have closed universe expand forever, you can have anything. And what's going to happen depends on the future behavior of dark energy. What dark energy decides to do tomorrow or in the future will drive how our universe is going to end. And now you realize the importance of understanding dark energy, its nature, because if we do that, then we'll be able to decide what the universe is going to do in the future. If we don't understand the nature of dark energy, we don't know the fate of the universe. Well, even more weirdly, under certain circumstances, and I can tell you what they are, we'll have a big rip. This is an event that's going to happen depending on what dark energy does in maybe 20 billion years or 100 billion years or less. When first galaxies, the space will start expanding so rapidly, accelerating, that first the galaxies will get ripped apart. Then a little bit later, stars will get ripped apart. Then a shorter time later, planets will get ripped apart. Then our houses and atoms will get ripped apart moments right after this, and then a tiny moment after atoms, the fabric of space itself will just go pew, and get ripped apart. And this is bizarre but true. It's called Big Rip. And for those of you who are aficionados of dark energy, this happens if the expansion is even more rapid than that for vacuum energy. If the energy density of dark energy is not vacuum, but if it grows in time. If it doesn't fall, is not even constant, but if it grows in time, the energy per cubic foot, then this will actually happen. And finally, bizarre consequences. This is more solid. Even if dark energy is vacuum energy or something not as exotic that would do the big rip, galaxies are, in the normal matter-dominated universe, we see more and more galaxies because as we wait, because what happens is the light has more and more time to reach us, so we see more. In the accelerating universe, not true anymore. Now the universe is expanding so rapidly, it's accelerating, that light cannot catch up with the acceleration. And so, in fact, we are losing galaxies from the sky. Fewer and fewer of them, as you wait for, cosmological timescales, will be in the sky. So maybe in 100 billion years or so, the sky will be empty. There will be nothing other than, there will be our galaxies that's holding together, and that's going to be it. Sky empty, not literally. There will be stars from the galaxy, but there won't be other galaxies in the sky. So these are some bizarre but true consequences of dark energy. Okay, so I went off there, but let me do, and unlike my students, unfortunately, you don't have little Quiznum clickers where you can vote, but you can just vote for yourself and decide. So here's the little test. Is dark energy similar to dark matter? Not a very precisely asked question, but let me pose it anyway. Yes, no, or in the distant past only? And the answer is no, not at all. Dark matter is attractive. Dark energy is repulsive. Yes. Dark matter is clumped. Dark energy is smooth. Right? So very big differences. So even though we'd like to lump these two all in one and kind of try to explain two things with one explanation, in practice that doesn't work well at all, at least so far. They're so different that so far people have really needed to follow two separate lines of effort to explain dark energy. Okay, so now the question is, what do we do to find more about dark energy, to learn more? So, the cutting edge area of research now is a comprehensive program of various cosmological observations, and as you can imagine, at least one talk could be just devoted to those. Many of them are indirectly sensitive to dark energy. One of them is, of course, measuring distances to supernovae. Some others I haven't mentioned, I might in a slide or two, are gravitational lensing, distribution of galaxies in the sky, any type of probe. When you look at cosmology, you look at distant universe, you measure distances, you measure hot and cold spots in the cosmic microwave background. Remember that picture of the anisotropies? That's a good probe of dark energy as well. Right now, we don't have any idea how to look for it in the lab, but that may change. Okay, so no ideas how to test it in the lab on Earth. Near-term goal is to find out global properties, what goes under the name of expansion history of the universe. How rapidly is the universe expanding? Just describe it if we don't understand it. And the ultimate goal is to understand the nature and origin of dark energy. And this will require, some very smart people to get more data to look at them and then be able to decide. So a little more on that. So I mentioned already, in addition to supernovae, distribution of galaxies, probe of dark energy indirectly. Gravitational lensing, which I'm sure was mentioned in some lectures, this is bending of light around massive objects. How much light is bent and all the details of this depend on dark energy, depend on the expansion rate of the universe. Cosmic microwave background I mentioned, and abundance of galaxy clusters. How many of these gigantic objects you see depends on, if the universe is accelerating, for example, it's diluted enough, so maybe you expect fewer galaxy clusters per unit volume. And Gus Eberhard has given a talk about galaxy clusters here a few weeks ago. So that's one possible probe of dark energy. There's a lot of theoretical work going on. Searching for an explanation from fundamental particle theory, string theory, people who work on gravitation. And so far, it's fair to say there wasn't much success in this area, but that may change, hopefully, sometime soon. Right now, we don't know how to look for in the lab. I've mentioned this already. Okay, so many experiments are being planned in the near future, next 10 years or so, to try to understand dark energy. This is now considered as more or less a premier problem in cosmology, together with maybe a few others. And the ultimate experiment, maybe one of the most ambitious efforts, just happens to be one in which University of Michigan is involved as well, and it's called the Supernova Acceleration Probe of SNAP. SNAP is a space telescope that's going to be launched and observe supernovae. So here's a telescope. This is a primary mirror. It's a 2-meter telescope, 2-meter mirror. to go out and look for thousands of supernovae. So more and better is the key. More supernovae and better accuracy. And also look at things like gravitational lensing and distribution of galaxies. So all of those things I mentioned before, done from space where atmosphere doesn't get in the way. So you can always see really well. Now, let's see. I will now have to exit this application and go to another. I will show a movie about SNAP. And let's see if it works. So here's the video of, okay, here's a launch somewhere in 2013 or 2014. Delta IV rocket takes off and it carries experiment into the orbit. Now, there's various things going on. There's different parts of the rocket splitting off, and please don't ask me which one is which. I don't actually have any idea. But engineers are taking care of this, so it's in good hands. So there's different parts splitting up. Here is the experiment, and I think now it's going to separate. Oh, it's getting boosted. So it separates right around here. And now what it's going to do is open its fairings and look in the sky, finally. It's been protected so far. So it looks at the sky, it looks at very distant supernovae. So now we have this incredible zoom you can only do in a movie. In a galaxy far, far away, we'll have a type 1a supernova. And the supernova is going to be bright. Actually, here's now white dwarf accreting matter from a companion. So it's accreting. And at some point, it's going to explode. Now, this tremendous explosion is going to be as bright as a galaxy almost. In the movie, it's more. And it's going to be seen by the telescope. So now the telescope sees a light. Here's a primary mirror. Any light hits it. Secondary mirror. It's going to go through the hole. In the middle, it's going to hit the tertiary mirror. And it's going to bounce through the filter set into the detector. This part is designed and partly built in University of Michigan detector, very much like your digital camera, but much bigger and better. Okay, and so here's the data that's being sent back to Earth. So this is observation of a type 1a supernova from SNAP. Okay. Okay, so this is the near future. So let me conclude on that note. Let me say that dark energy was directly discovered around 98, and it's one of the most momentous discoveries in cosmology, and some people would say all science. Its origin and nature are very mysterious. We are at the early stage of understanding dark energy. It makes up about 3/4 of the energy density. It's roughly or exactly unchanging with time, and we'll try to decide which. It makes the expansion speed up, and I've talked about two famous problems. Why now, and why cosmological constant problem, the most famous, why is it so small, and yet not zero? It's one of the biggest mysteries in science, and let me also say that for the next 10 years or 15 or so, we are guaranteed fantastic returns from these experiments like SNAP. We will understand much better the expansion rate of the universe, and we'll be able to describe global properties. Whether we understand the nature of dark energy, we hope we see that solved within our lifetimes. It's a big problem. It will require some very smart people to think and for better data to be there, first of all. Thank you.
Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. Lois Tiffany Endowment, and by gifts from friends of the program.